Okay, showing the road type, so to speak. Geometry notes, 10.6, that's where we're sitting at today. We're checking out circles, diameters, radiuses, central angles. You guys should have that down right now. We've had that exposed. The general form or direction that we're going to go. Circle basics. Okay, we're going to talk about diameter, radius, and central angle. Congruent circles, semicircles, major, minor arcs, adjacent angles and arcs. I should say adjacent arcs. Arc addition postulate, circumference of a circle, which is 2 pi r, or diameter times pi, and then arc length, and we're going to talk about that with fractions, our friends. Okay, so now here's the deal. When we're talking about circles, it's a set of all points that are equidistant from the center, and that center is, located here, and that's how we name a circle. So if I have this as circle C, okay, maybe I'll talk about it as circle C when I write it down notation-wise. I just won't write out circle. Okay. Now, diameter is a segment that contains the center. Now, I'm just going to slide this over here a little bit because I got diameter right there. And the diameter is the distance across the circle. You're going to find out that the diameter is a chord whose endpoints are on the circle, and it goes through the center. Okay. Now, as I'm going on, I'm talking about a radius. The radius itself is a distance from the center out to the edge of the circle, and that is the one thing that defines a circle as we talk about it. And that's why a circle is similar to all other circles. You can't say that about any other shape, or few other shapes, I should say, because we can talk about squares that way. We can talk about isosceles, it's not isosceles, equilateral triangles that way, because they only have one measurement. So all equilateral triangles, all circles, and all squares are similar to all others, okay? Because of that solitary one measurement we need to define them. So as we're going through radius of a circle, we also have something called the central angle. We've talked about central angle before. Central angle, and when we're talking about that in a polygon, the central angle of a polygon goes from the center of the polygon to the vertice, two consecutive vertices of the sides of the polygon. Now, it's the same thing in a circle, except now I don't have to count up how many sides a circle has, because it doesn't have sides. It has degrees, and the circles are 360 degrees total. Okay, and we can have a central angle as small as we'd like or as large as we like, up to 360. Okay, and the central angle defines our arc it intercepts, and we're going to talk about that. But I'm just going to outline an arc here. This is the arc that's intercepted from the green central angle, and those are the things we're going to be talking about next. Okay, today's objective is to find the measures of central angles and arcs, to find the circumference and arc length. So that's where we're going. Okay. Now, congruent circles have congruent radii. Now, radii is the plural for radius, okay? And semicircle, a type of arc, is a half circle, okay? And named by its endpoints, also the endpoints of the diameter and another point on the arc. A minor arc is smaller than a semicircle, named by its endpoints. And a major arc is larger than a semicircle, okay? And we're going to talk about those right now. I've got a couple examples, but I'm going to highlight them as we go. The first one is a semicircle, and I'm going to use blue for this. Actually, I'm going to use red for that semicircle. I've got RSI, RSI, or ISR. Please keep in mind when we do these, the two outside letters, when we're talking about a semicircle or a major arc, are my endpoints of the arc. The inside letter lets you know which direction around the circle you're going. So if I'm saying just arc ISR, I start at I go to R by way of S, okay? So I always want to go by way of the middle letter if I have a middle letter. It gives me the direction. If I'm looking at a major arc, okay, that's another three-letter moniker. My major arc here I gave you as RIS. Well, if I'm going from R to S by way of I, R-I-S, I'm going to S, starting at R, by way of I. Okay, going to S, starting at R by way of I. So I just have to follow around. And make sure you go in that order as you Go. It makes it easier. It lets you know it's larger. But if you have 3 letters as part of the name, you're talking about a semicircle or a major arc. If I just have 2 letters, like I do with that RS, that's my minor arc. Okay, so I'm talking about the shortest distance. So I wouldn't go to the big one. I always have students go, boom, which one is it? I was like, is it 2 letters or 3? It's 2, it's the shortest one. Is it 3 letters? Yeah, then it's the longer one because that's the longer name. Okay, that's as we go. Questions about this? We're good? Make sure you have these little sub descriptors on minor and major arc because that'll help. Okay. Now, naming arcs. Again, a minor arc, it's like AD. A semicircle has the endpoints of the diameter in it and one other letter between them. So I'm going to give you an example, DAC. I got DC coming across here. Let me erase those so it's not confusing because we use that for some questions people asked. I've got DC and I could go DAC, I could go DEC. Those are 2 different semicircles, okay, incorporating DC, right? I just gave you one example. I would like you to find as many as others you can. What are the major arcs? A major arc, as I go through, I got C, D, A is a major arc. Anything beyond 180. How do I know I've gone beyond 180? These are diameters coming through here. DC is a diameter, AE is a diameter. They're there to kind of help me know what's a major arc and a minor arc and a semicircle. Here's an example, okay? Questions right now? Alexandra? Is that a question? Liar. Okay, all right, we'll come around. All right, I'm just picking on you a little bit. Interesting face that you gave that look. What I want you to do first, A, answer as many minor arcs as you can. Go. And after you do the minor arcs, go ahead and do the next ones. Fill those out. It takes us about a minute and a half to do these. Okay. How'd you do? Now remember, if you went DA, it's the same one. Okay. It's not like, oh, I found 8 of them, bloom. No, it's still the same arc. Okay. It's just another way to name it. Okay. They're not different. Are we all right? Make sense so far? Okay. Now what I want you to do is talk to somebody next to you, left or right, and compare your semicircles. Go. Talk to them. Say hi. Remember, part of this is you having given the opportunity to discuss it with somebody else. Oh, okay. Yeah, I can take that. Okay, so how'd you do on them semicircles? You okay with them? Did you find all those? I mean, there's 4 because there's 2 diameters. There's 2 semicircles with each diameter. The other side, you know, both sides of that diameter. So since I have 2 diameters, I should have had 4. Okay. Now, major arcs. Major arcs are bigger than 180, smaller than 360. Okay. Major arcs are bigger than 180, smaller than 360. Check them out. Check them out as we get going. We okay? Is it making sense? What makes a minor arc, a semicircle, and a major arc? Okay. Now, key concept for this, as we go through, measure of a minor arc is equal to the measure of its corresponding central angle. The measure of a major arc is the measure of the related minor arc subtracted from 360, and the measure of a semicircle is 180. And people are like, what? So let's step through each one. The measure of a minor arc is equal to the measure of its corresponding central angle, which means this. RT, the measure of arc RT is equal to 50 degrees. That's the central angle here. So if I wanted to, the measure of angle RST. So those two measures are the same. The arc measure and the central angle are identical. Okay? If I tell you the arc measure is 90, I know its central angle is 90 as well. They're the same measure. Now, in order for me to find a measure of a semicircle, that isn't hard. If I'm doing a semicircle, this is a straight angle, right? So that's 180 degrees. Semicircles, degree, 180. That's where that comes from. Now, the measure of a major arc, let's talk about that. The measure of a major arc. Let's talk about the arc that they actually have written down there. We're looking at the arc RQT. I'm going to find the measure of arc. Notice how I do that arcing segment. It's an arc, RQT. So I'm going around the circle. I'm using blue, going around here, RQT. How big is that? The total degree around a circle is 360. So I know it's 360 minus, I did not cover this segment, and that was my measure of arc RT, and we found out earlier that that was going to be 360 minus 50. Okay, so as I'm going, I know that my arc measure is 310. Okay, now it's the same one that I've got right here. I just wanted to make sure you recognize where that reasoning came from, so I thought I'd step it through as we did it. Are there any questions about it? Really, it's adding and subtracting with a purpose today. Okay, do you know that? I'm adding and subtracting with a purpose. That's what I'm trying to get across. Okay, so as I'm going through, keep in mind, I'm just adding stuff or I'm subtracting some things. Adjacent arcs are arcs of the same circle that have exactly one point in common. Adjacent arcs can be added together just like we did with angles. Remember, we had angle addition postulate way back in chapter 1, first semester? Well, we can add the arcs together, okay? It'd be very similar. So now, we've got this arc addition postulate, okay? Very similar. Matter of fact, let's put in an example. If I knew that AB was 40 and say BC is 140, okay, that would represent AB being 40, and I would just add together BC 140. Sorry, I was going to write the measure of angle BC. 140. Now keep in mind, they have a point in common there, right? Are you okay that I came up with 180? That's all I'm doing. I'm just adding stuff. And the arc angle measure is based on the angle measure of the central angle measure. Does that make sense? We're good? All right. So what I want you to do is take this time and come up with these arcs. Now, this has been really tough for folks, so I'm gonna slow it down a little bit and watch what we've got. JBH is a straight angle. It's a diameter. That means this arc is 180 degrees. That would further mean that this angle is 180 minus 151, which equals 29 degrees right there. This is 90 because of this. This is 90 because it's the other part of 180. Now all I want you to do is piece together those values to come up with the other measures we have, okay? Are there any questions about what I've got you going and doing right now? Okay, all right. Okay, there are some folks that are kind of paralyzed of what we're doing. GJ is this arc. It is intercepted by this angle, so GJ is 90 degrees. GJI, GJI, okay, GJI is going around. It's 90 plus 151. 90 plus 151 is 241. That's where 90 plus 151 comes from. 90 plus 151. Okay, that's GJI. HGJ. HGJ is that. It's a semicircle, 180. HJI is a little tougher. I'm going to get rid of this stuff. I do know that this is 29 degrees. HJI is everything on the circle but the 21 degrees. So that's me 360 minus 29, which is 331. You okay with what I'm doing? I'm using the idea of addition or subtraction to find my arc measures that are identical to the central angle measure that defines those arcs. Okay? Go ahead and finish out the other 8 if you haven't done those so already. Finish out the other 8. Okay, if you got questions, tag me on them. We'll see what's up. Oh. Okay, turn left, turn right. Check out your stuff with somebody else. If you're at home on the video, talk to the mirror. I got a really good friend. They look just like me. Okay, how you doing? How am I doing? Check them out. You just spray Mr. Heightshoe with that sneeze? Okay, all right. For a minute there, I was like, I thought that was her sneeze. That's why she was so embarrassed. And poor Heightshoe just got a shower, but no, that wasn't the case. You did it right. Okay, good. Thanks for covering that sneeze. Well, you might have done something that deserved that water bottle being thrown at you. Have you ever thought about that? She's just getting back at you. She's that vindictive, I guess. Or maybe not. She couldn't be because all right, so questions. Are we okay? Remember, if your numbers and my numbers are different, we got to talk because it's not just how you feel about the problem. They're either right or they're not. Okay? So now, flying on. We're talking about circumference of the circle. Okay? Circumference is the distance around the circle. C equals 2 pi. R. R really defines our circle. R is used for perimeter. By the way, circumference is a fancy schmancy way to say perimeter. Okay? It's just the distance around the circle. And we just use one value, radius. That's all we need, and we have circumference. Okay? Well, we could also use diameter because two diameters, or two radiuses make a diameter, I should say. And you got to keep in mind that we can adjust our circumference formula to be diameters times pi. One thing I want you to know about, though, is that pi is the ratio of circumference to diameter. Okay, circumference divided by diameter gives us 3.14159. Pi is irrational. It can be written as a terminating or repeating decimal It cannot be written. It won't terminate, but we can write it that way. We can say, hey, well, you can write 3.14. Okay. Or we can go, 22/7, it's close. Okay. I'm going to let you in on a secret. You've used those throughout your life. I've seen them on worksheets. I am looking for you to use one of these two values. And I'm going to let you in on a secret. How do you know which one? Okay. This key is in your calculator. Pi key. You should be able to find it quite quickly. It has a much larger value than the 10 or 8 spaces that your calculator will display. Okay. If I am taking ACT, SAT, MCA, you are expected, unless they tell you differently, to use your Pi key. Okay. You are to use your Pi key unless you're told to use 3.14 as pi. Okay, because your answers in a multiple choice situation will be adjusted for those values that you're using. So make sure you're using your Pi key. And that's the best thing I can do. Your Pi key in your calculator will be located in an area that looks like that. It'll be on a key or just above it, and you got to press a second key to get there. Now, as we're going through today, we're talking about a circumference of the circle, which again is the distance around. And let's go back to, we've done the circle basics. We've talked about congruent circles, semicircles, major, minor arcs, adjacent arcs, arc addition. Now we're at circumference. We got circumference and then we got arc length, and we're done with notes today. Okay, so we've got about 7, 8 problems left. In Theorem 10.9, circumference of a circle, the circumference of a circle is pi times diameter or pi times 2r. Okay, because diameter is 2r, okay, as we go through. So what I'm asking you to do in this next section is just take the formula we just learned about, use the one dimension you need, radius. Okay, you need radius. Okay, so I got 16, I pop it in, 16 times 2 is 32. I am done. If I ask, this answer is in terms of pi right now. Matter of fact, I put units on it and I'm done. If I ask for in terms of pi. But in this case, I didn't. So I would accept in terms of pi or you to round to the 100th. Okay, if I don't. And there we go, 100.53 if I pop that in my calculator. Okay. Now, sometimes you'll be given a diameter in a problem. And remember, a diameter is just two radiuses that went the opposite directions. So I can, according to our theorem 10.9, write the circumference in terms of diameter and pi by just popping my diameter in. It's 22 pi. I'm done. In terms of pi, I'm finished with the problem. And I could even put in and say, hey, that's meters. Okay, but again, I accept that too, 69.12 meters. Okay, you guys go ahead, do C, and look left, look right, and see what that other person came up with. Are you okay with your C? Now, I want to talk about this because I was really loose about this. We're going to pull this over here for a second. I want you to pull out your calculator. I want you to find, if you've got graphing calculators, you on the third key down on your left, third key down on the left, you have the math key. Okay, if you press that key, well, first of all, let's put in 13.6, then go to that key, and then find frac on the math key. Go to the math key, hit frac, okay, and hit enter. Your calculator will return a fraction, okay? Well, that's 136 over 10. So I'm just going to do the fraction real quick in my head. 136 over 10, okay? If I move the decimal, it's 13.6 over 1 is the same as 136 over 10, which is 68 over 5. Really, if I'm going to do it in terms of pi, 68 pi over 5 is my answer. That's the same answer. And I want you to know that when you make that change, okay, that's using your calculator if you're going to do it in terms of pi, and it's not going to be a pretty answer, okay? Now, a warning. You cannot leave it as a fraction if you multiply the number by an irrational value, like by the square root of 2, the square root of 3, any type of square roots, or any irrational value like pi. If you multiply anything by pi, your calculator will not be able to leave it as a fraction. But if you pull the pi value out of your calculator, you got a good chance of it becoming a fraction, okay? So just make sure you recognize that as you're going through. And I'm showing you that because this next section, I'm going to ask you to do it in terms of pi as we go. Sir, can I help you?
No, never mind.
Okay, all right, thank you. As we're going through this next section, concentric circles are coplanar circles that have the same center. Now, I want to bring this back to track, okay, for obvious reasons about concentric circles, and here's why. When you're asked to run just a lap of the track, and you are given the choice of whatever lane to run in, which lane would you pick? The inside lane, right? Why? It's the shortest distance around the track, okay? Well, when we're talking about concentric circles, and we're talking about the distance that we would cover in concentric circles, because the distance, the track distance, it made different on the curves, okay? If I ran in outside in lane 8, I would be running further around the track because of the curves, not the straightaways, okay? But it's the curve that's the issue. And those people on track know what a 2-turn, 1-turn stagger is and why. That adjusts for that difference, okay? What I want you to realize is that because of that, the inside part of the curve versus the outside part of the curve is smaller, okay? And people are like, well, okay, that makes sense. But the same central angle defined both those arcs, okay? So they have the same arc measure, they just have a different arc length. And that's what we're going to be working on next. I'm not going to do problem 4. We're going to save that for Monday. We're going to go on here, and we're going to get to 6 here. I'm going to get you going on notes real quick. And we're going to talk about fractions after that. So if we were going to share a pizza, okay, and you had your turn at the pizza and you saw that much gone, this much left, okay, how much of the pizza did I eat? I got some people saying 1/4, I got people saying 90. Okay, explain yourself, 90. Why did you say 90? I kind of led you there. Okay, 90 degrees because of this little marking right here, okay? And I purposely did that because it's amazing to me when we talk food left in pizzas, everybody's really quick to go on 3/4, half, and 1/4. I mean, almost immediately, okay? But when I put it up on the board as really fractions, they're so fraction phobic, they're like, they won't say a thing. But I love it with pizza. But let's go about that. 90 out of 360. If I divide that, if I use my fraction key in my calculator, and please try it right now. Some of you know how it is. 90 goes into 360 4 times, so it's going to be a 4th. I want you to practice your fraction key move. Go 90 divided by 360, hit your math key, select 1, hit enter, and hit enter again. And you should have your calculator return actually 1/4. Okay, and your graphing calculator will never give you a mixed number. It'll always be a fraction or improper fraction. And an improper fraction is the number on top is bigger than the bottom one. But I want you to recognize that I ate 1/4 of this pizza. okay? And so you have 3/4 left, okay? We are going to be working with that type of fraction of degrees. And we're going to be talking about today the crust that's left. I ate 1/4 of, if let's talk about a thin pizza, you know, where the crust is really hard and brown and crunchy, okay? Well, that's the part that we're measuring, okay? We're measuring that percent of the circle around, because 1/4 is 0.25. 25% of the crust of this circle has been eaten, okay? 75% of the crust is left to be eaten. That's your part, okay? And that's really what this formula does, this length of arc AB. Because I put in the amount of degrees on top out of 360 as if it was a test out of 360, okay? The most the measure of arc AB could be was 360. 360 divided by 360 is 1. That's the whole distance around the circle, okay? But any portion less than 360 is going to be a percent of the total. So it's going to be less than the whole circumference. So that's what we're doing here. That's what this formula does. It breaks it down. And so I have, and we'll talk about this in pizzas. I have 180, right? But isn't that half a pizza? It's half, right? A semicircle is half. So I go 180 divided by 360 gives me half of 16.4. And remember, I know how to use my fraction key in my calculator. Remember. 180 divided by 360 times 16.4. Math key, frac, enter.
There's no math key on my calculator.
Okay, for those folks who don't have it, I'll show you the fraction, the decimal key, the F double arrow D. And there should be a F double arrow D. It's in this area. I just got to pull up my glasses because I can't find it.
Double arrow.
See that double arrow on the problem? You got to use that, and that's what you can do. Okay?
What?
So this is what's going on. If I got TI 30X, I can put in that information. I can go 180 divided by 360 times 16.2. That's what it is there.
Okay.
I hit enter, and it gives me that. Well, I go to my second F double arrow D, hit enter, and it gives me a mixed number 8 and 1/10. But what I could do as I go through this is I can go from an improper fraction or mixed number to an improper fraction, hit it again, and get that, and it's 81/10. But then I can reduce it and it becomes, actually it should have been 82/10. I don't know why it was 81/10. Should have been 82. Oh, 16.2. I put in 16.2, not 16.4. That was my mistake. So you go ahead and give it a try and see what it is. It should have been 16.4 in, okay? And make sure you can get it, because you should be able to get the 41. Remember, this is all about not including, you don't include the pi in this. It's all about getting the numbers, and then you just slap the pi alongside on the top of the numerator, okay, to get the final answer here. Are there any questions regarding? Your turn. Do this one. By the way, the blue shaded or the blue highlighted areas are the arc measures, arc length I should say, that I want you to find. The arc lengths I want you to find. Length is the distance of the arc. Measure is the degree of the arc. Okay. Go ahead, do number 2. Go ahead, do number 2, or letter B, I should say. Okay, so keep in mind, I've got my AB, my arc I'm looking for is 120 out of 360. That's where 120 came from. Okay, so 120 out of 360. Okay, that'll give me a third of my circle. Okay, the distance of the arc, the length of that arc, a third of the circle. And I'm doing it in terms of pi. I'm just going to go, hey, 6 pi. I did an intermediate there, so you can see why it was a third. So I got 6 pi inches. And if I use my calculator, it's much quicker. Okay. Make sure you show the formula. Make sure you show the numbers that you're putting in. Every time you have a formula, you should show the formula, show the numbers you're going to be putting in. So then when I'm grading your stuff, I can tell if you, hey, had fat fingeritis or you just don't know how to use it. Okay. So it helps both of us to get things going. In C, remember my arc measure, the degree measure I'm going to use is 315, 360 minus 45. Because I'm not interested in that 45, I'm interested in the rest. So I'm going to pop that in that way and get it going. So you guys go ahead, do C and D, and see where it's going to end up for us. Hi, kiddo, what's up? No, I just want this arc. Yeah. Oh, that's just the radius right there. That's the radius. Okay. And, letter D in problem 5. The 15 is the radius. And we'll finish out C here. And I've got 35 pi. Are you doing okay with 35 pi about what's going on? Okay. Now, in this last one, I want to make sure that you recognize this is 60 degrees. It's across from this central angle. The central angle and the arcs that it intercepts or defines is the same value. So I've got this as 60. Because of vertical angle theorem, this also is 60. And therefore, the arc that's highlighted in blue is 60 degrees as well. So keep that in mind as we're working. We're using that vertical angle stuff. We're using complementary, supplementary angle stuff. All that stuff comes back to be useful. Okay. So I'll be popping it in my formula, getting it working on 60 out of 360. And I got 5 pi. Now, there's a lot of folks that have made a mistake and probably flipped things around, and like especially in C, they found 45 out of 360. Okay, and consequently you found it was 5 pi. Okay, it was just a mistake. You just forgot the other part of it. That's all. Just make sure you make those corrections. You can pay attention to what you're supposed to find. Now, on Monday, we will finish the remaining of this notes. We will go over our Chapter 6 assignment questions and some highlighted Section 6 assignments questions and some highlighted Chapter 5 assignment questions because we may have time to finish most of it, but not all of it today in class. Okay, so we're done with notes, and hopefully things are going well. You got questions? Make sure you make it in the class.